Hello and welcome back to this series on trusses. In this lecture, we're going to discuss several aspects related to the behaviour and design of trusses. So far, we've seen how to check if a truss is determinate, how to identify zero-force members, and how to solve determinate trusses using both the method of joints and the method of sections. We'll start with the behaviour of trusses. We'll consider the behaviour of the following trusses: a Pratt truss, a Howe truss, a Warren truss, and a Fink truss. Let's start off by looking at the behaviour of a Pratt truss. This truss has both vertical and diagonal members, where the diagonal members are directed inwards, that is, towards the middle of the truss, from top to bottom. Here you can see a numerical simulation carried out with a computer software GSA. The simulation shows the response of the truss to loads moving on the bottom belt. The loads represent vehicles. Each time the vehicles are longer, a longer part of the truss is loaded. The simulation shows the development of internal forces in the truss members. Tension is shown in shades of green and compression is in shades of red. Additionally, the thicker the element becomes, the larger the internal force. It can be concluded from observing the internal forces in the computational simulation that the top belt members are always in compression, while the bottom belt members are always in tension. The vertical members located towards truss ends are always in compression. Some verticals around the applied loads can be in tension, but the tension force is relatively low. The diagonal members towards truss ends are always in tension. Some diagonals around the applied loads can be in compression, but the compression force is relatively low. And in the centre of the truss, the verticals and diagonals can carry both tension and compression. Now let's look at the behaviour of this Howe truss. In this truss, the diagonal members are directed inwards from the bottom to the top. The computational simulation shows the response of this truss to loads moving on the bottom belt. Here again, tension is shown in shades of green and compression is in shades of red. Pay attention to the forces in the truss members. Let's have a look again. The observations of the internal forces in the computational simulation show that the top belt members are always in compression and the bottom belt members are always in tension. The vertical members located towards truss ends are always in tension, and some verticals around the applied loads can be in compression, but that compression force is relatively low. The diagonal members towards truss ends are always in compression, and some diagonals around the applied loads can be in tension, where the tension force is again relatively low. In the centre of the truss, the verticals and diagonals can carry both tension and compression. As you can see, the different arrangement of diagonals in the Pratt and Howe truss results in different distribution of forces. The diagonal members are the longest members in these trusses. Therefore, Pratt truss is more efficient structurally because the diagonals are in tension. Now let's look at the behaviour of this truss. This Warren truss only has diagonal members which are directed inwards from both top to bottom and from bottom to top. This computational simulation shows the response of this truss to loads moving along the bottom belt. Pay attention to the forces in the truss members. Let's have another look. The observations of the internal forces in the computational simulation show that the top belt members are always in compression, while the bottom belt members are always in tension. The diagonals directed towards the load from bottom to top are always in compression, while the diagonals directed towards the load from top to bottom are always in tension. The diagonals under the load can be in compression or in tension. Now let's discuss the structural idea implemented in a Fink roof truss. Many roofs are inclined to prevent water pooling and reduce snow piling. Therefore, we will start developing a roof truss from a triangular shape. The truss is loaded by the self-weight of the truss members. In addition, the rafters, that is the inclined members, are loaded by the weight of the roof. This is the combination of the described loads. The truss bars will bend and deflect under these loads. Where the rafters deflect, excessively due to larger loads applied. The deformed shape of the truss will not be able to provide an appropriate support to the roof. To decrease the deflections, the inclined members can be supported by struts connecting them to the horizontal member. These struts will transfer part of the load from the rafters to the horizontal member. As a result, the horizontal members will also deflect excessively. To decrease the deflections, the horizontal member is supported by ties at the connections with struts. As you can see, the resulting structure is much more rigid than the initial triangular one. The addition of struts and ties created new load paths. As a result, bending of members in this truss was substituted with compression and tension. In this distribution of forces in the truss, tension is shown in shades of green and compression in shades of red. Additionally, the thicker the element becomes, the larger the internal force. Let's conclude our observations. Centres of rafters in the Fink truss are supported by short struts in compression. At each third of its length, the points of horizontal members are held up by long ties in tension. Tension forces are transferred by the ties into the rafters at the top corner. These forces become compression forces in the rafter. Under the applied loads, the rafters want to slide apart. The movement of the rafters is constrained at supports by the horizontal member, resulting in its higher tension. Trusses are planar structural elements. As a result, they have to be constrained from out-of-plane movement. Let's discuss how this is achieved in construction. Tension members are self-stable. That means they stay straight. Compression members can lose stability and therefore are designed to resist buckling. You can see an example of buckling in the picture on the right, where the compression members deform while the tension members stay straight. In trusses, the entire top belt is in compression, and therefore it must be braced to an adjacent truss to keep straight. To prevent the loss of stability, trusses are restrained by bracing, outriggers, or stiff connections between truss and roof, floor, or deck. For bridge trusses, it is ideal if the deck is connected to the top chord, but this is not usually practical as it limits the space under the bridge. Here you can see the bracing arrangements for Fink roof trusses, which include longitudinal binders, chevron braces, diagonal wind braces, and temporary braces needed during the erection stage. Let's try to understand how the braces work. Basically, braces and parts of trusses form complex trusses working in the direction perpendicular to the truss, preventing the loss of out-of-plane stability. In the roof shown here, the longitudinal binders combine with the chevron braces and the short struts in the trusses into a structure. This structure provides stability to compressed rafters at the points of connection with short struts. The diagonal wind brace combines with a longitudinal binder, the wall, and the rafters into the following structure that keeps trusses from falling sideways. When out-of-plane stability is not provided, compressed truss members buckle, and entire trusses can collapse sideways. This often occurs during the erection stage. Here you can see a system of roof trusses. The trusses are connected by many braces. Let's highlight a few longitudinal binders. And let's now highlight a few chevron braces. In this picture, you can see a steel roof truss during erection. The trusses are currently connected by one longitudinal binder. Additional binders will be installed later at these places. Bridge trusses consist of two planar trusses on either side of the bridge deck. Let's consider this railway bridge with a through truss. Each truss in this bridge is confined at the bottom belt by the deck. The top belt is restrained by a non-planar truss. In this truss, the vertical members are in compression, and therefore the long vertical members are restrained by vertical trusses against buckling. This is a deck truss supporting a road bridge. Each truss in this bridge is confined at the top belt by the deck. The bottom belt is confined by a non-planar truss. In addition, the compressed long vertical members are confined by vertical trusses. Let's move on to discuss some aspects of safety in the design of trusses. Failure of just one member in a statically determinate truss will generally cause its complete failure. This occurs because the statically determinate truss has only one load path. To increase the number of load paths, additional elements are provided, making the truss statically indeterminate. In statically determinate trusses, loads in truss members depend on their relative stiffness, where tension members are much stiffer than compression members. Failure of just one member in a statically indeterminate truss leads to rerouting of the loads to another load path. Therefore, the members in these trusses should be designed to be able to carry larger loads. Otherwise, consequent failure of overloaded members can occur. This type of failure is called progressive collapse. Here you can see the collapse of a bridge truss due to the failure of one minor gusset plate, leading to overloading and sequential failure of additional members, resulting in the collapse of the bridge. Progressive collapse is a very fast phenomenon. Truss members are designed to carry compressive and tensile forces. These forces are called primary forces. In design, joints are assumed to allow for free rotation of members. However, real joints do restrict rotation, leading to the development of moments in the members called secondary forces. The secondary forces are usually ignored because they're much smaller than primary forces. The weight of truss members is also usually ignored in design because it's much smaller than the forces in the members. When the weight of members is considered, it is applied at the end of each member, just like external forces. To increase the resistance to buckling, compression members are designed with larger sections. Additionally, long compression members are restrained along their length. Let's look at what happens to a statically determinate truss when one of its elements fails. The failure of a top chord member leads to the formation of a mechanism. This mechanism consists of two parts of the truss connected to supports by pin joints and connected together by a common joint at the bottom chord. The failure of a bottom chord member results in the formation of a similar mechanism with a common joint at the top chord. The failure of a diagonal divides the truss into two smaller trusses connected by two bars and four pin joints. This structure represents another type of mechanism. The failure of a vertical has the same effect, resulting in the formation of two smaller trusses connected with two bars and four pin joints. And now that we've learned to consider some additional aspects of truss design, join me in solving some